What else is there to say about derivatives with logs? So there's this technique known as logarithmic differentiation. And it's going to help us take derivatives of these two examples that you see here. So what if we had y equals x plus 1 raised to the x? That'll be the simpler one. We'll also look at this more complicated one, more intimidating one. Y equals the sine of x raised to the square root of x. Oh my goodness. Okay, so notice, what do these functions have that we haven't seen before? We have a variable being raised to another variable, right? Variable, and then variable here in the base and a variable in the exponent. So we've been doing like x squared, x to the third, the fourth. We've had a variable raised to a number since the beginning. We know how to do those. And then we just learned exponentials, where this was the constant and the variable was up here, right? A to the x. We know how to do that. But when it's both, well, that's a whole new ball game. We don't know what to do with this. There's no rule for this. None of those other none of the other rules apply here if we have a variable raised to a variable. Let's write that. Variable raised to a variable. All right. So it turns out there's really not a rule here, since it's the combination of two other rules. We need to change the approach completely. So that's logarithmic differentiation. Okay, let's get into it. One thing we need to remember that we're going to take advantage of here, there's this law of logarithms, and I'm just pointing out one of the laws. The log of m raised to the r with base a. So if inside your argument you have something raised to an exponent, and here I'm talking about they could be variables, they could just be all constants. Whatever the case, if you've got an exponent happening here, you can move that exponent down as a coefficient. Remember this law? And now that we know calculus, like that almost feels like you're taking a derivative. Okay, but you're not. That's just one of the rules, one of the properties of logarithms. If there's an exponent there, it can move down in front as a coefficient, and they're equal. Okay. So here's what we're going to do. We're going to go for it. We're going to work through that first. We're going to work through both examples. And I think it's good to do two of them just because this is a very technical procedure, and you see it once, and you're just trying to wrap your head around it. Then you see it again, and it really helps to solidify the process. Okay. Find dy over dx using logarithmic differentiation. Okay. Let's start with y equals the quantity x plus 1 raised to the x. How are we going to even begin? What is this? All right, there's no logs. You're like, there's no logs here. What? We're going to take the natural log of both sides. We have to do this ourselves. If you see a variable raised to a variable, or if you're just told to do it this way, take the natural log of both sides. Okay, so right there, the natural log of y equals the natural log of x plus 1 raised to the x. Why would you do that? Okay, because by introducing the logarithm here on the right side, we can use that property of logs. We can take this x and move it down in front. So we'll keep the left side as the natural log of y. That x moves down. We no longer have variable raised to variable. It's now a product. Okay, what comes next? We're going to use implicit differentiation. There's a method to the madness. To learn logarithmic differentiation, we did need implicit. Okay. So, I'm not going to write when we learned implicit, I would always write d over dx, applying to both sides. I think we understand that. The derivative with respect to x of both sides. Okay, so how's that going to work? Let's look at the left. If you take the derivative with respect to x, then you need the chain rule on the y. So natural log y, the derivative would be 1 over y, but then remember you always got to multiply by dy over dx. So here on the left, the derivative 1 over y times dy over dx. How about the right side? This is a product. X times the natural log of x plus 1. So let's look at that product rule. Well, derivative is 1, copy, plus copy the x, times, and now this is a chain rule of a fairly simple one, but I do have something more than just x in there. So the chain rule would say 1 over that times the derivative of x plus 1, and that derivative is just the 1 plus 0, if you will. Okay, so here's the derivative of natural log x plus 1. We're well on our way. We're doing pretty good. Let's clean up this right side before we go any further. And that's the end of this page for me. Okay, so get rid of the 1. I'm going to put that x up on top. Okay, that looks a little bit neater. We're very close to the answer. We want to know dy over dx. We want to solve for this. That's what we do with implicit differentiation, right? Okay, so we're going to multiply the y on over there. Let me include this page again. There we go, there we go. Okay, so multiplying the y over, we've got y times the whole thing, big parentheses, natural log of x plus 1, plus x over x plus 1. Okay, we're not going to stop here. We started with a function. We want to end with a function. We don't want this y in the final answer. Well, what can we do about it? So it turns out we know what y equals. Right? At the very beginning, the function is y equals x plus 1 raised to the x. So we can make that, if they're equal, we can substitute it. So we can change this y back into x plus 1 raised to the x, and there's our final answer. X plus 1 raised to the x times the quantity natural log x plus 1 plus x over x plus 1. We got that derivative, and that is a monster. But, well, that's the way it goes. Kind of something cool that happens with that, though. When we take the derivative of x plus 1 to the x, it does repeat itself, which is kind of interesting. But then it's multiplied by the product rule between, well, it's actually between x and the natural log of x plus 1. So there you are. Okay, let's go through this same procedure again, but for our more difficult example. Again, I think seeing it 2 times will be helpful, and we'll be able to kind of streamline the process, okay? A little bit. We'll refine it a little bit. All right, y equals the sine of x raised to the x, and we can see variable raised to variable. How do we get started? Take the natural log of both sides. Why do we take the natural log of both sides? Because we want to move this exponent down in front. That's the whole reason. It's the only reason why we do it. That allows us to do this, and now we've got a product. Okay. Once we have it written this way, then we're going to take derivatives. And you notice on the left, it's always just going to be natural log of y. So, oh, my mistake. I forgot. I getting a little ahead of myself, getting a little excited. I went ahead and rewrote square root x as x to the 1/2. Okay. All right. Okay, now let's take derivatives. Notice on the left, it's always natural log y. So when you take this derivative, it's always going to be 1 over y times dy over dx. And on the right side, it's always going to be this product for a product rule. So we've got the derivative here times that plus this one. Okay, I don't want to move too quickly if you're trying to copy this while I'm speaking. Okay, derivative, copy, plus copy. And then this derivative, well, no surprise, that's a chain rule. So it's 1 over sine x times the derivative of sine x gives us the cos x. And now at this point, I'm going to clean up the right side a little bit. It's a bit of a mess to me, so I'm just going to keep that left side the same. And do this right here. So I've got 1 over y dy over dx. This part, 1 over 2 x to the negative 1/2. I'm going to tuck that underneath the natural log of sine x. So that goes to the numerator. These go to the denominator as 2 square root x. This is kind of personal preference at this point. We could keep it just the way it is here, multiply the y over at this point. But I err on this side just because this looks so much better to me than that. But they are equivalent, and not we can't argue this is simpler. That's not simpler. Just looks a little bit better, I think. And then I'm going to take this and make it square root again. And cosine x over sine x is cotangent x. It's not wrong to keep it as cosine x over sine x. You can do that. But why not just make it cotangent x? Okay, so that looks better. Then we're going to multiply the y over. And finally, we're going to turn this back into the original function. So here, the derivative dy over dx equals the sine of x raised to the square root of x, because that's y, times the quantity natural log of sine x over 2 square root x plus square root x cotangent x. That is it, logarithmic differentiation. Okay, good luck to you in the homework.